All right. Hello, everyone. My name is Michael Carilli. I'm an applied cryptography engineer at Matter Labs. We're building Zksync elastic network. And today I would like to talk about the RiscV prover with full GPU acceleration that we've built that powers the elastic network under the hood. So we're going to talk about the history, how we got here. We're going to talk about what we prove. We're going to dive into the math, the proof workflow, and then give you some details of the GPU acceleration and some preliminary benchmarks. So how did we get here? Back in 2003, Zksync era was the first EVM on mainnet, or the first ZK EVM on mainnet. Shortly afterwards, we introduced our first industrial-grade proof system, Boojum 1.0, which was Stark-based that proved our EraVM bytecode. Then just this summer, we launched the Elastic Network, our flagship sort of chain of chains where every chain can be fully customizable while sharing liquidity and offering fast, trustless cross-chain transactions. So now we want to sort of turbocharge the Elastic Network with two things. At a higher level, there is Boojum OS, which is a multi-interpreter environment that supports native EVM equivalents as well as continued EraVM support. And my friend Antonio Locascio over here is going to give some talks on that later. And under the hood, we want to be able to support a massive network of chain of chains. So we want a fast general purpose prover. And we want to decouple, we want it to be proving general purpose code, RiscV code, so that we decouple the protocol upgrades in Boojum OS from the prover upgrades. So here's a teaser of the performance numbers that we're achieving, the raw GPU segment proving numbers that we're achieving. And if you're following the evolution of RiscV provers, you will know that these are pretty solid. So I'll get into more detail on that later. So what do we prove? We prove RiscV 32-bit I plus M, which is an integer instruction set with the extension for multiplication and division. Only kernel mode for now, so no user mode. And we also require aligned memory accesses. But for present purposes, that is adequate. And then for the verifier, which we also need to create proofs of for recursion, since that is fully under our control, we can optimize the instruction set a bit further. We, for example, remove signed ops and subword memory accesses, and it's more efficient. And on top of this, we have delegation circuits or precompiles for common operations that aren't RiscV but are expressed in handwritten constraints that are more efficient. And we have some for Blake 2 and big integer math, and some others that we're still working on internally. And we're able to efficiently communicate back and forth between the delegation circuits and the main RiscV circuits. So a bird's eye view of Boojum 2.0 is it's a start prover with a maximum constraint degree of 2, which unlocks some nice little features. For example, because the zero fire in the constraint quotient is degree n for or n-1 for some terms. It turns out the max degree of the constraint quotient is n-1, which means that we only need to evaluate on one coset to compute this, which means the only evaluation domains we need are the main domain and one coset domain. So that makes the prover overall pretty fast. And then for the arithmetic itself, we use Mersenne31, which is known to be very efficient on 32-bit hardware like CPUs and GPUs. And for NTTs, the number theoretic transforms that are used for polynomial interpolation and evaluation, we came up with this neat trick that involves sort of synthesizing some different topics from the literature. The problem with this Mersenne31 field is that it does not contain a lot of powers of 2, so it's not an FFT. It doesn't provide an FFT-friendly domain. But there was this paper from, I think, Ulrich Habach, who figured out that if you sort of augment it if you pick a subdomain of the complex field, a second degree extension, you get this so-called circle group that has this very high two-adicity that makes it perfect for the FFT domain. And it turns out that because this has the same properties as the complex numbers that we're familiar with from real analysis, it pairs nicely with FFT tricks from the real analysis FFT literature, and we can sort of do these so-called 2-for-1 NTTs. We can take two columns of M31 values, transform them to one complex column, and then transform them to two M31 output values. So that's nice and efficient on GPU. And this code is not open source yet, but I posted a write-up in case anyone is curious. And if you're following the circle group literature, you might wonder if this is a true circle stark. The answer is no, but it's fast, so we're going to ship it, and we're going to try circle starks later and see if they're more or less performant. So we also use this efficient memory argument drawn from the two shuffles make a RAM paper. Maybe there's some others that involves constructing a read set and a write set. And each read and write has an address and a value and a timestamp associated with it. And we make this giant, and we sort of, the write terms all go in the numerator, the read terms all go in the denominator, and the whole thing is sort of collected into one big product. And it turns out if we enforce that for the program's actual accesses, which are one write divided by one read, if we enforce that the write timestamp is greater than the read timestamp, then the only way you can fit it together is if the write, or as if each read to a particular address cancels out the most recent write to that address, which is really cool and kind of mind-bending to think about. But yeah, I highly recommend looking into that a bit more if you're curious. So our trace is divided up into the setup columns, memory columns, and the witness columns, where the setup columns are fixed for the program. They contain the program binary and some lookup tables. The memory columns contain the memory argument stuff, as well as the stuff that's needed to unlock the delegation circuits. And then the witness columns contain the bulk of the runtime values that are used to prove the RiscV cycles. And we typically run with 2 to the 20 to 2 to the 22 rows per segment to saturate the GPU, although for beefier GPUs we can run more in theory. So for large programs, they may run for more than 2 to the 22 cycles. So we need multiple segments to encompass all the cycles. And for such a proof, it proceeds in 6 phases. First, the setup that is fixed from the program. Then we do execution phase to get the RiscV execution trace. Then we do what's called a memory pre-commitment, which I'll explain more about shortly. Then we do the actual Stark witness generation. Then we proof segments, and then we do recursive verification. So going through each of those phases. Oh, there we go. And this segment here, the Stark witnesses and the segment proving, is the most compute intensive part of the process. So for setup, we just create this setup table with a program binary and lookup tables. And every proof segment is just going to get an identical copy of this, and it is known to the verifier. And then for memory pre-commitment, the memory argument actually spans the entire program. So the values, the values that we consider RAM or register values, that memory argument needs to be consistent across the entire program, which means that the challenges we use to construct the memory argument need to be based on values drawn from the entire program. So what we do is we pre-compute. The first thing we do is we compute the memory argument or the memory columns for all segments, and then we commit to them to get a Merkle root to draw challenges. And the memory columns are, so this is kind of like a bottleneck that must be overcome before we can do segment proving, but In practice, it's a relatively minor overhead because the memory columns are a small part of the overall trace. So once that's done, we can generate the Stark witnesses for the entire program, and this can be totally parallel at this point. Currently, we do it on CPU, but we're going to port it to the GPU soon. And then once that's done, the segment proving can proceed fully in parallel across segments. We can put each segment on a different GPU and create a proof for each segment. And then finally, we combine the segments via recursive verification. So we run the verifier over the proofs for all the segments. We collect the verifier execution trace, which is smaller than the original execution, the original program's execution trace, so it creates fewer segments. And then we sort of proceed. We prove those segments, run the verifier over them again, until we're down to a single proof that effectively verifies the entire original program. So how does this actually look on the GPU? Well, it turns out that if we have enough CPUs to saturate the device via the witness generation, the pipeline witness generation for each segment, we can actually get really, really good device utilization. And here we see a Insight Systems profile of such an example. And you can see that we're overlapping the host-to-device copy of the next iteration's witness with the proving of the current iteration's witness. And you can see that this is on a NVIDIA L4. We can totally hide that latency and basically keep the GPU constantly busy with work. And again, this requires that you have enough CPU cores to saturate, which can be challenging for beefier GPUs. And so we plan to. It's more convenient to put the witness generation on the GPU, which we will soon. But you can see this is a pretty good timeline. And another thing I want to emphasize is that almost this entire system is in-house CUDA, written by myself and my boss, Robert Remen. We wrote our own hand-optimized NTTs, Blake hashing, lookup and memory arguments, composition quotient evaluation, barycentric evaluation, deep quotient, Frye folding, as well as a number of pointwise utilities and transpose, bit reverse, stuff like that. So returning to the rudimentary benchmarks that I showed from the teaser, we'll go into a bit more detail. This is performance on single GPUs, so a single L4, a single 4090, a single 5090, and a single H200. And this is raw proving speed, so just the proving of the segments themselves, right? No recursion, no precompiles, no final snark wrapping. So it is rather rudimentary. And it also requires that we have enough CPUs to saturate the devices, which is challenging for the big ones, to say the least, and probably not practical for production, which again, we're just going to move that to the GPU soon anyway. So that bottleneck will be eliminated. And actually, for some of the systems that we tested, we were bound by not by the witness gen necessarily, but by the speed of PCIe transfer, because the PCIe is what transfers the device from the host to the CPU. And it turns out that PCIe connection was not fast enough to feed the GPU. So here you can see for a couple of the systems is the performance we observed, shown in blue, and the dashed line shows the performance that the GPUs are capable of, if you remove that PCIe bottleneck, which we will once we have the witness gen on the GPU. So this is a minimal benchmark. It's rudimentary, but it's very promising. And we do have all of these building blocks written: the recursion, snark wrapping, some precompiles, and we have the capability to prove segments in parallel. We're still putting all those pieces together. I want to do some comparisons with SP1 and RiscV. I've talked to them about that. Ultimately, we would like to do end-to-end performance comparisons for real Ethereum transactions, as well as some more minimal comparisons of the proving process itself. But we need a little bit more due diligence because we want to be fair to everyone involved. So yeah, that's pretty much it. And you guys can scan this QR code to, if you're interested in hearing more about this later in the week. Antonio and I are going to give a joint talk on this at, I think, the ZK Hub Hacker House. And Antonio himself is going to give a talk on Boojum OS, which is the execution environment with EVM equivalents that this is going to power. And also, I recommend our CEO's keynote on the Elastic Chain, which will be at ETHDender itself. And all of those can be found via the QR code. So thank you very much for listening, guys. And yeah, I encourage you to scan the link if you're curious. And here's the references in case you want to dive into any of the math that I sort of skimmed over. Any questions? When to use this when mainnet? Well, like I said, we're feature complete as far as the prover goes, and as far as recursion and snark wrapping. We still have a number of optimizations potentially in flight, and we're still figuring out which of those optimizations we would want to include. I would like to ship as soon as possible. As far as the entire system goes, it's that's above my pay grade. maybe one of you guys has a better idea. Antonio knows because he knows more about Boojum OS.
Let's say this year, but not at the end of the year.
Okay, so Antonio says within the year, which is a conservative estimate for sure. Dustin?
So a question on the comparisons coming for SP1 and RiscV.
Mm-hmm.
How do you, what's the kind of plan to be able to compare apples to apples? Like what parameters would be considered part of the comparison in benchmarking?
Well, that is a can of worms because, of course, the systems are different in many ways. Ultimately the only true standard would be a representative set of user-facing transactions, like the price, the latency, or the cost per transaction, the cloud cost per transaction of a representative set of Ethereum transactions, which involves fitting the entire system together with all the moving parts, everything fair game, precompiles, recursion, snark wrapping, L1 data, the whole 9 yards. That is, that's the ultimate goal, and that's the ultimate standard. But there are also some pieces that we can compare apples to apples, such that are permitted by all of our APIs. And in particular, one of the minimal things we can compare is segment proving pipelined with witness generation, because all of our APIs permit that. They're SP1's, RiscV's, and ours. And it's sort of apples to apples. So the figures that I presented would be an upper bound of what we might expect for our performance in that scenario. With the, well, it might be equivalent because we have beefy enough. If we throw beefy enough CPUs, at it, we can saturate. We can saturate and reach those performance figures. But the number of CPUs that we need to do that is so large that it wouldn't be super practical for production. So for such a comparison, I would target just the L4, where a modest number of CPUs is required to saturate, where the number that I showed, I think it was 5.7 megahertz, is more realistic for production. So yeah, that's still not quite doing them justice entirely, because they also have more infrastructure than we currently do to parallelize the segment proving, and we're still building that out. But I'm gonna try and have this more nailed down by my second talk at the end of the week.
I imagine it has to be almost a coordinated effort with those other.
I did. I've talked to them. I've talked to them extensively. I talked to John Guibas at SP1, and I talked to Lucian at RiscV extensively on Telegram to coordinate this and nail down that these particular API calls are actually doing this under the hood, and so they're on board with this particular minimal benchmark as long as I'm clear about the areas in which the additional capabilities that they have, and this is not fully representative of a production case. Any other questions?
So I guess that when we open source everything, will other protocols like Polygon, if they want to, will be able to use this program?
Well, it is RISC. It's a RiscV prover, so presumably anybody who wants to prove RiscV code could use it. We might be able to even coordinate with people who have more of the high level infrastructure in place to use this. I think one thing we might want to add before then is user mode. Right now, as I said before, we only have kernel mode. So in order to run untrusted code, we would probably want to add that. So in theory, the answer is yes. In practice, we'll just have to see what the demand is.